In the middle of Canada's Baffin Island sits a piece of the last ice age that should normally spend much of the year buried beneath bright snow. But in July 2026, satellites saw something different. The snow disappeared unusually early. By the middle of the month, almost the entire Barnes ice cap was exposed as bare ice. Turquoise meltwater ponds appeared across its surface. Dark channels carried water toward its edges. NASA described it as the earliest the ice cap had become this bare in the satellite observations used by researchers. That matters because snow is not just decoration on a glacier. It is armor. Once that armor disappears, the ice underneath begins absorbing more sunlight, melting faster, and sending more water away from the ice cap. What happened on Baffin Island this summer is therefore not simply an unusual satellite image. It is a glimpse of a feedback that can turn an early melt season into an even more destructive one. And Barnes ice cap is not an ordinary glacier. It is a surviving fragment of the Laurentide Ice Sheet, the enormous mass of ice that once covered much of northern North America. Today, Barnes covers roughly 5,700 square kilometers of central Baffin Island. In places, the ice is about 730 meters thick. Imagine a slab of ice almost as tall as the world's tallest skyscraper, spread over an area several times larger than a major city. That is what remains. To understand why the loss of snow matters so much, first consider the difference between snow and ice. Fresh snow is extremely bright. Much of the sunlight hitting it is reflected back toward the sky. Bare glacier ice is darker. It may still look bright to human eyes, but compared with clean snow, it absorbs significantly more solar energy. This difference is called albedo. High albedo means more sunlight is reflected. Lower albedo means more energy is absorbed. So the transition from snow-covered glacier to exposed ice changes the amount of energy entering the surface. And that creates a feedback. Snow melts. Darker ice appears. The darker surface absorbs more sunlight. The ice warms. More ice melts. More dark surface becomes exposed. NASA observed exactly the ingredients needed for this process on Barnes ice cap in 2026. The ice cap entered summer with an unusually thin snowpack. Within only a few weeks, that snow was largely gone. By July 12, Landsat 9 images showed a vast network of meltwater channels stretching from the interior toward the margins. Bright blue melt ponds were scattered across parts of the surface. From space, the channels resemble veins spreading through the ice. But they are not passive markings. They are drainage systems. When snow remains on a glacier, some meltwater can soak into the porous layers below the surface. That partially compacted snow is called firn. Water entering firn can sometimes freeze again. When it refreezes, some of the water stays on the glacier instead of escaping. But once the seasonal snow and firn are lost, meltwater behaves differently. It runs directly across bare ice. Existing channels widen. Smaller streams connect to larger ones. Water moves toward the edges of the ice cap much more efficiently. NASA notes that this means water that might otherwise have been retained and refrozen can instead be quickly removed from the glacier. The difference sounds small until you remember the size of Barnes. Thousands of square kilometers of exposed ice can collect enormous volumes of meltwater. And the drainage network already exists. Many of the channels return year after year. Think of the difference between rain falling onto dry soil and rain falling onto a city covered with roads and storm drains. The first landscape can hold some of the water. The second moves it away rapidly. A bare glacier increasingly behaves like the second system. The earlier this drainage network activates, the longer it can operate during summer. That is why timing is so important. Barnes ice cap has become nearly snow-free during previous summers. Researchers noted examples in 2019, 2020, and 2024. What made 2026 different was how early it happened. An ice cap losing its snow in September has only a short period before autumn temperatures return. Losing it in July potentially exposes bare ice to weeks of additional summer sunlight. The same glacier can therefore experience very different amounts of melt even if both years eventually become snow-free. This is one reason scientists pay close attention to the length of the melt season rather than just the final appearance of the glacier. But the 2026 images are only the latest chapter in a much longer retreat. Research cited by NASA indicates that Barnes' ice cap thinned by roughly 1 meter per year between 2000 and 2020. Over approximately the past 4 decades, its margin retreated around 4 meters per year on average, although individual sections changed much faster. One area along the central southern margin retreated more than 400 meters, averaging roughly 10 meters per year. Satellite images reveal the result as exposed brown terrain surrounding the shrinking ice. This newly uncovered ground has been hidden for extremely long periods. Barnes exists because the Laurentide Ice Sheet once dominated much of northern North America. At its greatest extent during repeated ice ages, Laurentide ice covered millions of square kilometers. As the climate warmed after the last glacial period, the vast ice sheet retreated. Barnes' ice cap eventually became one of its isolated survivors on Baffin Island. For approximately the past 2,000 years, its size was comparatively stable. Then modern warming pushed the system into sustained decline. Scientists have gone even further back by studying rocks around the ice cap. When ice covers rock, cosmic rays from space cannot easily reach the surface and create certain isotopes. Once the ice disappears, exposure begins. By measuring those isotopes, researchers can estimate how often particular rocks were uncovered during past warm periods. Those records produced a striking result. Barnes appears to have shrunk to approximately its modern size only a few times during the past 2.5 million years, and complete disappearance seems to have been extremely rare. That makes the current retreat scientifically important. The ice cap itself is not large enough to create dramatic global sea level rise if it disappears. Researchers have described its direct contribution as relatively small compared with Greenland or Antarctica. Its importance comes from what it represents. Barnes is a natural experiment. It is a smaller ice body responding to the same basic physics that affect much larger ice sheets. Temperature rises. Snow cover decreases. Bare ice absorbs more radiation. Meltwater becomes more efficient at draining. The ice surface lowers. And as the glacier becomes thinner, more of it may occupy lower, warmer elevations. This can make continued survival increasingly difficult. There is another feedback hidden inside glacier motion. NASA research tracking hundreds of thousands of glaciers has shown that Barnes' ice cap speeds up during summer as surface meltwater reaches the base of the ice. Water can temporarily reduce friction between the glacier and the underlying ground, allowing the ice to slide more rapidly. The effect is not as simple as more water always meaning faster ice. As summer continues, drainage channels beneath glaciers can become larger and more efficient. Water pressure may then decrease, allowing friction to increase again. But the discovery shows that a glacier has something resembling a seasonal pulse. Warm weather does not only melt its surface, it can alter how the ice moves. And researchers found that seasonal glacier speed tends to increase with warming, providing another signal of how glaciers respond to changing climate. Barnes therefore contains several connected processes. Snow controls sunlight. Sunlight controls melt. Meltwater controls drainage. Drainage influences how much water is lost or refrozen. And some of that water can reach the glacier bed and temporarily alter ice motion. What looks from space like a simple white patch is actually a moving hydrological system. The 2026 images made that system unusually visible. With the snow removed, old layers and surface textures appeared across the ice. Meltwater channels stretched in branching patterns toward the margins. Blue ponds formed in depressions. And surrounding the shrinking ice cap, increasingly wide areas of exposed land recorded where the ice used to be. There is no reason to assume one early snow loss year alone determines the future of Barnes' ice cap. Weather varies. A future winter could produce more snowfall. A cool summer could reduce melting. Glaciers respond to conditions accumulated across many years. But Barnes is already experiencing a long-term negative trend, and models published years before the 2026 event projected that the ice cap could disappear within several centuries under a range of future emission scenarios. That prediction makes the new satellite images especially striking. Scientists are not simply watching a hypothetical future. They are watching individual stages of the process. First, the seasonal snow becomes thinner. Then it disappears earlier. Bare ice is exposed for longer. Meltwater drains more efficiently. The edges retreat. The surface lowers. Year after year, a feature inherited from the last great North American ice sheet becomes smaller. There may eventually come a summer when the snow disappears and never returns to enough of the surface to reverse the decline. Barnes ice cap survived the disappearance of the enormous ice sheet around it. It survived thousands of years of natural climate variation. But in July 2026, Landsat saw it enter summer almost completely bare earlier than researchers had previously observed. The most important thing in those images is not the blue meltwater. It is the missing white snow. Because once the protective surface disappears, the summer sun is no longer melting snow. It is melting the ancient ice underneath.